Hello everyone and welcome. This is Giannis with Ververica and this is a video about getting started with Apache Flink and Fluss. So for those of you that are not familiar with Fluss, there's going to be a link in the description below that goes more into detail around it. But in short, it's a new columnar streaming storage layer working great with Apache Flink that we have created in order to solve some really interesting problems when it comes to streaming data and new real-time data analytics. So in this video we'll see how you can get started with Fluss. We're going to go into some benefits with hands-on examples on what it does and how you can use it. And so we can get started. This is what we're going to building in this video to see all those things in action. So we're going to create an end-to-end application that basically surround gameplay events. We are going to have different data generators that generate data regarding games. And our goal here, and to see all these things in action, we want to calculate for every game the top 3 players. And after we also have these tables, as you can see here, our leaderboard, this data that is being calculated in real time will be ready to be queried from query engines like Starox, for example, to power real-time dashboards. And at the same time, we'll see how these tables can automatically be offloaded onto your data lake and create a data lakehouse. We'll see all these things right now with Apache Paimon, and for those that are not familiar with Paimon, it's basically a new table format that the Flink community is working a lot with, and it's all about the real-time and streaming data use cases. It solves some really interesting problems when it comes to streaming data onto your lakehouse. So without further ado, let's get started and slowly see all these things in action. But while we're here on this diagram, some important things to keep in mind is that we'll have 3 tables. So basically when it comes to Fluss, we don't play with topics here, or rather we play with tables, which is something that everyone is familiar with on the real-time analytics world. So basically, compared to a topic, a table is directly queryable, and we have 2 types of tables in Fluss. We have the primary key tables, as you see here, which basically similar to a database. They have a primary key, and for each key you always have the latest update, but they also have similar to a database that has the bin log and keeps track of all the changes that take place onto the table. It also keeps track of that change log to know what changes take place on each key. And we also have the log tables, which is exactly similar to an append only log on Kafka. The data is append only, and instead of partitions here on Fluss we have the concept of a bucket, and so the parallelism similar to topics. It is defined by the number of buckets you have, and you can also guarantee strict ordering guarantees and processing within the same bucket, similar you will do to a partition. So we will have player events, gameplay events that get generated on our log table, and this is going to generate an append only immutable log. And then we'll have player profiles, as you can see here, and games. And these are primary key tables, so for each key here we have the player ID, and here we have the game ID. We're only interested in the latest value for that particular key. Then we'll run a query that calculates the top 3 leaderboard based on our gameplay events, and then we'll use a top 3 leaderboard enriched table, which is going to have all the results but enriched with information from player profiles and games. What is interesting here in Fluss is basically it's like having Kafka and Redis functionality within the same system, because you're also allowed to run a high performance query per second streaming lookup joins. So instead of having to relay an external cache, you have all these things built in, and you can run streaming joins to enrich your data with dimension tables directly within the same system. So let's see all these things in action, and hopefully everything will start making sense. So the first thing here, I have my Docker Compose file, which you can use to actually get started. So here we have the coordinator server, which is used by Fluss for coordination things. And then we have the tablet servers. The tablet server is similar to a broker. So basically this is what keeps all the replicas of the tables and feeds data back to the clients. And as you can see here, some important things here on the properties. I'm also enabling to use our Lakehouse, and right now Paimon supported, but after the next release, more table formats like Iceberg, for example, will be supported. So you will be, or Hoodie, so you will be able to use whatever Lake format works for your use case. And here we have 3 tablet servers, as you can see, and a small Zookeeper instance. And then we also have our Flink cluster, which basically consists of one job manager and a task manager. This is our Docker Compose file. I'm also doing some volume mounts here, so we can actually inspect what is going on in the file system to get a better understanding. Now, my Flink cluster here also uses a custom Docker image I have, and basically builds on the Flink 1.20 image, and it just adds some connectors here. I have the required dependencies for Apache Paimon, which also requires some Hadoop dependencies, and also have the Fluss connector for Flink for the 0.6 release, which is what we'll be using. And also I have Faker, which is going to help us to generate some data. So with that in place, let's go ahead and start all of our services. So I'm going to run here Docker Compose app. And so my cluster will start running. Let's give it a little bit, and with that, all my services are up and running now. Perfect. So I'm going to go on services here and just grab a terminal within your job manager, and let's go ahead and run the Flink SQL client. And then we have our guide here. So first of all, let me run these commands here. We're going to run with the default parallelism of 3, but this is also default based on your cluster configurations on your Docker Compose file. So first of all, I'm going to generate to create a player profiles table that is just uses Faker. It's backed by Faker, and it's going to simulate some data for player profiles. And just for the sake of demonstration, to see what this table looks like, I'm going to run a select all query here just to see some data. So we have a player ID, username, email, sign up date, and the counter of the player. So next I'm going to do the same for a games table here and see what the games data actually look like. Here we have the game ID, the title of the game, the genre, the release date and the developer of the game. And finally we have gameplay events. So let me also fix this here, and let's also see what our gameplay events look like. So I have the event ID here, the player ID, game ID, score, the event time, and the event type that takes place in a particular game. So this is the mock data we're going to be using. So let's see what we get again. So now let's get into the Fluss stuff. The first thing that we need to do is actually go and create a catalog, and this catalog is of type Fluss. As you can see here, we are also pointing to the coordinator server. So with that, let's go ahead and create our catalog and switch into using that particular catalog. And this is where we'll be creating all of our tables. So the first table, as we mentioned, is going to be about player profiles here. and it's going to have a primary key. This is a primary key table based on the player ID. And so we're specifying here that we want to have 3 buckets. It's like saying we want 3 partitions, just you know, to have a mind mapping between Kafka, if you're already familiar with, and tables here in Fluss. We're also saying that we want this table to be data lake enabled, and we'll see later what this actually means. But before also creating this table, let's also see some things here. Now here on my directory, I have these 2 folders for Fluss and Paimon. If I go into the Fluss, you can see we have all the data for the Fluss servers, the tablet servers. Just some, right now it's empty. We have some directories and some metadata files. We're not going to go into detail on those, but let's go and create our first table and see what happens. So with that, I have created my table here, and as you can see, a new Fluss directory is created, and this Fluss directory is going to contain all the data, and it's because we have 3 buckets. Each bucket is allocated on a different tablet server, and as you can see here, we have both a key value store and also a log store, because as I mentioned before, we keep track. We have both the cache, let's say, that has the latest a value for its primary key, but we also have the log, which is a change log that actually keeps track of all the changes that take place on that particular table, which is extremely important for downstream consumers. For example, if you're using Flink with Kafka, Kafka doesn't provide it out of the box. Rather, it has to rely on Flink state that can be expensive many times. And if you're consuming the same topic again and again, this changelog is going to have to be recomputed again and again using Flink state. Again, for more details, there is going to be a link video in the description, so make sure to see all those things that goes into more details around all those things and why they are important. So with that, I'm also going to start inserting some data within my table here, and I'm going to also create a games table that again is a primary key table with the game ID as the primary key. And I'm also going to insert the data here. And finally, I'm going to have my gameplay events table. The difference here is that compared to the other tables, as we said, this is a log table now, like an append-only log. It's going to act like an append-only log, exactly like Kafka. And because we don't have keys here, we're also specifying the bucket key, which is the player ID. So this makes sure that all the records for the same player will end up on the same bucket, and it ensures strict ordering guarantees for the same player ID. So let me go and create this table as well, and also insert some data. And also now, if I go to the directories here for the gameplay events, compared to the other tables, as you can see, it only has the log and it doesn't have a key value store. And so if I go now to my Flink web UI, I can see that all my jobs have started and have started generating data. So I'm going to pause here for a little bit just to leave these jobs running to generate some more data, and I'll be right back. Okay, so now that my jobs have been running for roughly 5 minutes now, I should have a fair amount of data, and we'll see in a bit of how much we have. For right now, and because if you go here, you will see we don't have many available task slots. What I'm going to do is actually kill the data generator jobs just to get to free up some resources and run the rest of the jobs, because each job here runs with a parallelism of 3. So I'm going to go to my player profiles and cancel this job. Then I'm going to go to games, cancel this job as well. And finally we have here the gameplay events, and I'm going to cancel this job again. And now I'm going to go back and continue with our application. So just as a reminder, right now we are at this place here, and we have populated these 3 tables with data. So the next thing we need to do is actually going to create a table that calculates the top 3 leaderboard. So I'm going to go back to my guide now and create this top 3 leaderboard game that's going to calculate all these things. It's going to be primary key table again, and the primary key is going to be the ranking and the game ID. So for each game we want to calculate the top 3 players. So I'm going to create this table now, and I have a somewhat long query here. Don't be intimidated by that. It just calculates every 60 seconds the top 3 players for each game. So I'm going to run this query and insert some data there. And the next table, as we mentioned, is going to be the same table but enriched with information about the users, the top 3 ranking users for each game, and also the game information. And again, this table is also has a primary key with the game ID and the ranking. So I'm going to run this table again, and here I'm going to run the streaming lookup join for both the player profiles and the games. And as we mentioned, Fluss provides some really high performance queries per second lookup joins. So I'm going to run this as well, and I have my jobs running. So if I go back to my Flink UI here, I can see that my job is running and it's processing millions of records for creating those tables. Now, before we move forward, there's another thing that I want to show you. So if you recall, both here on our Docker Compose file, we enabled the data lake format, and also when we created our tables, we specified that we want these tables to be data lake enabled. So if you check here, we have our Fluss cluster and we have this Paimon folder. Now in the future, this folder can be for Iceberg or Hoodie if you when we support more table formats, but for now it's Paimon. So let's see how we can actually and go back to the diagram here. We can get all these tables directly and automatically on our data lake as Parquet based files. So any query engine can directly query them. The benefit of doing these things is that first of all, we get better data freshness. So all the data here gets written within milliseconds of the tables, and then they get directly offloaded. So this means if you're also into this medallion architecture, that you're creating bronze, silver, and gold tables, and you either have to, because some table formats don't support streaming, you have to run like batch jobs that generate the other layers. Here you get data freshness of roughly 1 minute with Paimon, or 30 seconds, and all these things get created automatically, all the different layers, all these things, because basically they get offloaded from Fluss directly on your data lake. And the other thing is that because there's a good communication between the Lakehouse and streaming, what we call streaming and Lakehouse unification, we have this concept of union reads, which basically you can combine all the historical data from your Lakehouse with actual real-time data that lives on Fluss. So how we can actually get all this data on the Lakehouse? And the answer to that is the tiering service that Fluss provides. So what I'm going to do now is I have a command here, and I'm going to grab another terminal on my coordinator server and run this shell command, which basically just specifies that we specify the checkpoint interval which is needed for table formats, and here we have it on 30 seconds. So this means that every 30 seconds new data will appear onto your Lakehouse, and I'm just specifying that the whole service is going to run with a parallelism of 2. So with that, this means that the tiering service has started. And just to verify, if I go back here to my Flink web UI, you can see that I have a new tiering service job that started, Fluss Paimon tiering service. So if I look into that, it writes with a parallelism of 2, and basically starts offloading all the tables we have directly into your Lakehouse's Paimon tables. and the checkpoint interval is 30 seconds, so every 30 seconds we should see the data here. And also notice that we have specified a bucket number of 3 buckets for each table, and the same number of buckets also automatically gets allocated here onto the data lake. So you can see that there is also good mapping between the Fluss tables and Paimon tables. So right now we have created everything we needed. We have our real-time data, we have our historical data. So the next thing I want to show you before going into running batch queries is that, for example, let's go into our games table, and if you recall, this is a primary key table. So basically we're going to have, if we run the query also in batch mode, we're going to have the latest value for each key, but if you recall, there is also the changelog, so I want to demonstrate that. Let's go with something like 10,000, it should be sufficient, I believe. Let me also stop this job here, so I can make sure I have enough resources. So first of all, I'm going to stop this job here, and this job, and let's also stop the tiering service job. So if I go and run this query now, actually let's make it smaller, like 5,000 something. Yeah, okay, this is, I forgot there's some limit there. But this is not enough probably to see the full changelog, as we have lots of data. So let me go and remove the limit, although it might cause me some issues. So I can see the changelog, but just to make sure we see it properly, let me cancel the job again. So you see here all the, it might not be that clear to see. Let me try and kill this job. You can see the -u and +u, which starts for before and after. Because I'm streaming data on my console, it might be hard to see. So yeah, you can see that I have the -u, which is how the row looked before for that particular primary key, and how it looks after the updates, and the user information basically get updated. So this is the complete changelog we are getting. But because I cancelled hard here, I have to go back to my client, and let me go back here on the top. And what I want to do now is actually go down here so we can see some more interesting things. So I'm going to switch to batch mode now, and the first thing I want to see is my top 3 leaderboard and reach table. Oh yeah, sorry, I have to go back to my catalog first. So let me go up here and recreate my Fluss catalog, and go into that catalog, and let's run this query again. So if you can see here that we have our game ID, and for each game we calculate the top 3 scores and the top 3 players for that particular game. And we also have these records and risk with the user information and the game information, like the title, the genre, etc. So you can see how we can directly query, and because we also have the union rates, also combine the historical data and the real-time data. And these are things you can't do directly on Kafka topics. For example, you have to offload some kind of data lake and run your queries there. So let me also go and inspect, for example, the games table now. And if I also want, I can go to my player profiles, gameplay events, and for example, run the select count all from gameplay events, and let's call this as total events, and let me go around this query, and you can see directly we also get back and see how many records we also actually have within the table. Like we have 3 point something million records within our gameplay events. So again, the other thing we can do, for example, is let's say we have our game's data here, and for some reason we also did some errors in production, so I can go and grab a specific record and inspect it. And let's say for whatever reason this thing is wrong here, and the genre instead of puzzle here should be simulation. How can I actually easily fix real-time data with other solutions? And it's quite a pain, honestly, but in Fluss we can just run an update query directly. So if we go back and inspect our record, we can see that we directly on our streaming storage we actually updated that record. Or for example, if I go into my game profiles here, let's say for example we have this user here, this with email Erwin, and for this Erwin, for GDPR reasons, we don't have permissions anymore, and the user asked to completely delete him or her from the system. So how we can actually do that? I mean, again, with other solutions it might be hard to do so, but here we can just run a delete statement, and if we go back and run the select query, we can see that the user is no longer there. So you can see that how easy it is to reason with streaming data and real-time analytics with Fluss. And as I mentioned, it also brings many benefits when it comes to Apache Flink specifically, and currently we're working to also open it to more engines and support them. That's coming soon. So this was a getting started video to see some things in action, get your hands dirty with Fluss. So play around, and as always, if you like the project and the work we're doing, make sure to check it out on GitHub. There will be links in the description, and give us a star on the project. It will help a lot. So thank you all for seeing this video. I hope you found it useful and understood the benefits and the work we're trying to do to provide better solutions when it comes to streaming and real-time analytics. So see you soon, and thank you.